Yeah, so that's the same. So now.
All right, good morning, everyone. I hope you had a good weekend. So, the usual reminders, there's going to be a homework due on Friday. We're doing lab number 3 this week, and so there is a feedback for lab number 3, so please make sure you get that done before your lab section. And then the last thing is we have the hands-on bonus project. So if you plan on participating, the deadline for submitting your proposal is tonight at midnight. So I received a bunch of them over the weekend, so that is good. Okay, so what we've been talking about recently is the kind of energy type analysis for the interaction of charges in electric fields. And so we did a bunch of things. And so what I want to do today is I want to just take all of those concepts, which maybe seem a little abstract right now, and we're just going to do some examples. Some of them are kind of neat, I think, in my opinion anyways. So one of the things we talked about is this idea of electric potential. Electric potential was determined by taking the potential energy of a system and dividing by like the charge of whatever point charge you're interested in trying to understand. And so we gave it the symbol V. It also goes by voltage. And what we're able to do is to figure out a way of calculating changes in electric potential as we move through a region of space from some initial point 1 to some final position 2. And so actually, I see I have a little error here. This integral doesn't need a little circle. I'm just used to writing it from Gauss's law. So there it is. The integral of E dot ds, we follow some path from point 1 to point 2. And if we evaluate this integral with the negative sign in front, that tells us the change in electric potential. So one thing we could do is we could figure out the units of electric potential from this expression. The units of delta V are going to be equal to the units of the electric field times the units of ds, these little displacements. And so times the units of ds. And so that means the units of electric potential are electric field units. And so let's think about this electric field. We know that the force on a charge is Q times E. So E is force divided by Q. So that's newtons per coulomb. So electric field is newtons per coulomb. And ds is a displacement. And so it has units of meters. But a meter times a newton is a joule. That's an energy unit. And so this is equal to joules per coulomb. That's used so often, this idea of electric potential, that's defined as a new unit. It's defined as a volt. And so this is equal to 1 volt. Okay, and so let's see. Let's put this inside this little dash box. Okay. So from this expression, there's a bunch of other things we could learn about this electric potential. One is that the integral has a dot product in it. And so when we evaluate the dot product between this displacement ds and the electric field, if they're perpendicular to one another, that dot product will be 0. And so if you move perpendicularly to an electric field line, this electric potential is not changing. And so that's how you follow these lines or surfaces of equipotential, is you always go perpendicular to the electric field. Okay. And so we did an example where we thought about the electric field and these equipotentials for a point charge. And so the electric field lines are radial, and the equipotentials are these concentric circles with the point charge in the middle. For a point charge, the electric potential is Coulomb's constant, Q divided by R. So as you move further away, the potential gets weaker and weaker. If you wanted to have your equipotentials spaced so that the change in potential, delta V, was the same from each equipotential line to the other, they have to get further and further apart as you move away from the charge. And that's because the electric field's getting weaker. So the integral of E dot ds, if you have a smaller electric field, you have to take a bigger step, a bigger displacement to maintain a constant change in potential. Okay, so that was all calculating changes in voltage or potential from an electric field. You can go the other way. You can calculate electric field from a known potential. And we started with the work kinetic energy theorem to derive this result. And the result is fairly simple. The electric field along the direction S is given by minus the derivative of the potential with respect to S. And so by taking derivatives along different directions, you can find the various components of the electric field. So if you wanted the X component, you would do minus dV dx. If you wanted the Y component, you do minus dV dy. And then, so once you have those components, then you can go ahead and construct the electric field vector by taking the X component along the I hat direction and adding that to the Y component along the J hat direction. Okay, we also talked about the potential energy between a pair of point charges. It was a pretty simple result. It is just Coulomb's constant times the product of the two charges divided by the distance between them. This looks similar to like Coulomb's law for the force between these charges, but there are important differences. Coulomb's law is 1 over r squared. This electric potential energy is just 1 over r. And the other difference is that the Coulomb's force is a vector. So you have to specify a direction, whereas energy analysis is always just these scalar quantities. And so they're easier to work with. We don't have to worry about the directions of vectors. And then finally, the electric potential of a point charge, you just divide by 1 of the point charges. And so you just have one factor of a charge Q in the numerator. Okay, good. So that's sort of a summary of everything we've done in the past couple of classes. And so what I want to do is I just want to start applying some of those concepts and do some examples. So, example, we're going to start with 4 point charges on a kind of forming a square. So 1, 2, 3, 4, 1, 2, 3, 4, here we go. So here's 4 point charges arranged in a square pattern. I'm going to say that these particles all have mass m and charge q. And so these are all identical particles. And they're initially spaced so that the distance between them are all a. Well, so except if you were to go along a diagonal, then the distance between charges on a diagonal would be different. So the plan is we're going to assemble this arrangement of charges. So initially they're held in place at the corners of the square, and they're all at rest. And then we're going to, at some time, say t equals 0, we're going to release them. Because they're all identical, maybe they're all positive or they're all negative, it doesn't matter. There's going to be a repulsion between these like charges, and they're going to move off along diagonal directions. And so this one will move off in this direction, this one will move off in this direction, and so on. And the question is going to be, once these charges are infinitely far away from one another, how fast are they moving? Okay, so that's the question that we're going to try to answer. This is not a long diagonal. Here's the diagonal here. Okay, so I'll write down the statement of the problem and then we'll try to tackle it. So 4 identical point charges with charge Q and mass M are at rest at the corners of a square of side length A, sides length A, let's say. Okay, they're released from rest. So say at t equals 0, the particles are released from rest and they move away from each other due to the Coulomb repulsion. Coulomb repulsion. So the question finally is, how fast are the particles moving once they are infinitely far away from one another? Far away from one another. Okay, so there's a couple ways that we could try to tackle this problem. We could try to do a force analysis. That's not the best strategy because it's just extra work. The reason it's extra work is because as the particles move farther away from one another, the force between them is always changing. The force is proportional to 1 over the square of the distance between them. Moreover, it would be a challenge because if, say, I was going to think about the force on the charge on the top left corner, I have to think about the net force due to all 3 of the other charges, and they're all going to be vector quantities, and I have to add them, and I have to find the components and make sure, you know, there's some components that will cancel or some that are add. Even after all that, as the particle moves further away, the magnitude of that force will be changing. So it's possible, but it's a more difficult approach. So what we want to do is we want to do an energy analysis. Okay, so I'm going to break this up into a couple of steps. In the first step, what I'm going to do is I'm going to find the initial potential energy of this system. So find the initial potential energy of the system. Okay, so there's going to be like some U net. And let's go back to this picture and let's label the 4 corners. It doesn't matter what I label them. I'll just go clockwise around. And so we have corners 1, 2, 3, and 4, where we have all these identical particles of mass M and charge Q. So when we find the potential energy, we know the potential energy between a pair of point charges. So for example, if the problem was just to find the potential energy between point charges 1 and 2, we could do that. But then I also have the potential energy between 1 and 3, and 1 and 4, and 2 and 3, and 2 and 4, and 3 and 4. And so what we're going to do to find the net potential energy of the entire system is we're going to find the potential energy between all pairs of charges. So we have the interaction between 1 and 2, 1 and 3, 1 and 4, and 2 and 3, and 2 and 4, and 3 and 4. So we have the 6 pairs of charges. So we have 6 pairs of charges. So we're going to find the potential energy of each pair and then sum to get U net. Okay, so let's just remind ourselves how we would find the potential energy of one pair of charges. Let's say we're going to deal with potential energy between charge 1 and 2. It's going to be Coulomb's constant times Q1 times Q2 divided by, let's say, the distance between 1 and 2. I'll label it R12. All right, that's easy enough. If we go back to our picture, the distance between charge 1 and 2 is A, so R12 is equal to A. Q1 is just Q, and Q2 is just Q. So Q1 times Q2 is just Q squared. And so we're going to end up with, for this problem, Coulomb's constant times Q squared divided by A. And now what we could do is we could say, all right, I could do the exact same thing for, say, the interaction between 2 and 3. And the result's going to be exactly the same because all the particles are identical. And the distance between particles 2 and 3 is the same as the distance between particles 1 and 2. So if we go look at this picture again, let's see, U12, U23, U34, and U14 are all identical. So we have what? This is U12 is equal to U23 is equal to U34 is equal to U14. So those are all identical. And so that's 4 of our 6 pairs. The remaining ones are on the diagonal here. And so what's the distance between the first corner, corner 1, and corner 3? It's A times a factor. What's the factor that I need? √2, right? So it's just Pythagoras theorem. We have a squared plus a squared is 2a squared. And then we have to take the square root to get the hypotenuse. And so that's square root of 2 times a. So what we have is now the potential energy between charges 1 and 3 and 2 and 4. And they're going to be exactly the same, okay? Because all the charges are the same, and the distance between 1 and 3 is the same as the distance between 2 and 4. Okay. So U13 is equal to U24 is equal to Coulomb's constant Q squared. And then when we divide by the distance, we have to divide by √2. So finally, then, if we want to find the net potential energy, it's the first 4 are all identical. And so we're going to get 4 times KEQ squared divided by A plus 2 times the diagonal ones. And those diagonal ones contribute a little bit less because they're further away from one another. But we get something like this. And so that's it. That's the answer. We can write it in a bit of a nicer way. So we have common factors in our 2 terms. Those common factors are Coulomb's constant, Q squared divided by A. And then let's see, for the first factor, we need another 4. And for the second one, or the second term, I should say, it's 2 divided by √2. And so that's just √2. And so I think that should be the initial potential energy. Okay, good. What's the initial kinetic energy if they're all released from rest? 0. Okay, so then we know now the initial mechanical energy of the system. It's potential plus kinetic, but the kinetic energy is 0. And so the initial mechanical energy of our system is the potential energy plus the kinetic energy. And let's put initial here. But we already said this is going to be 0 because particles are at rest. And so let's say E initial is just going to be equal to this UI. And so let's call this UI. The net potential energy before the particles are released is UI. And so that's all just equal to this KEQ squared over A, 4 plus root 2, I think. Okay, good. So B is, let's find the final mechanical energy once the particles are infinitely far apart. Okay, once the particles are released, there's always going to be a repulsion between them, right? There's always like charges. Doesn't matter how far away they get from one another, there's always going to be that repulsion. Okay, so they're going to keep moving out further and further and further. How are the speeds of particles 1, 2, 3, and 4 going to compare? They're all going to be identical, right? All of the particles are identical. They were placed symmetrically on the square, and so there's no reason that one particle should be moving faster than one of the others at any given time. So because all particles are identical, they reach the same final speed. Let's just call it V. And so the kinetic energy at the end is just going to be 1/2 mv squared. But we're going to have 4 particles with kinetic energy. And so the 4 and the 1/2 cancel to give it 2 mv squared. All right. If we know that the potential energy between a pair of particles is K times Q divided by R, and then they're infinitely far away from one another, what's the potential energy once they move this distance? 0. Okay, so U final is going to be equal to 0 because U is proportional to 1 over R, and R has gone to infinity. Okay, so then the final mechanical energy is going to be K final plus U final, and that's just going to be equal to 2 mv squared. Okay, so the last part of this problem is just to find the final speed. So, find the final speed. Well, that's just conservation of energy. Conservation of mechanical energy is going to require that E initial is equal to E final. Okay, so E initial was this E Q squared divided by A, and I think it's 4 plus root 2, right? And then the final is all kinetic. There's 4 particles, so we had a 2 mv squared. And let's see, we just solve for v squared. Let's say v squared is equal to KEQ squared. We're going to divide by m, so it's m times A. We're going to divide by 2, so 4 divided by 2 is 2. Root 2 divided by 2 is 1 over root 2. And so finally then, taking the square root of everything, the final speed is kq squared divided by ma 2 plus 1 over root 2, and all of that is in the square root sign. All right. So that's one example of using conservation of energy principles to solve this kind of problem. You know, if you want a challenge, see if you can do this using force analysis. It'll be much more difficult, but you should ultimately end up with the same final answer. All right, any questions? Yep.
Would it be possible to work with only one particle?
Only one particle. So then I guess what you're going to do is you're going to find the initial potential energy of just that one particle and then the final kinetic. Yeah, I think that will give you the same answer. Yeah. Yeah. Anything else? Okay, let's do another example. What I'm going to try to do is, you know, one of the things that I like about physics is that if I solve one problem for one scenario, often the method we use can solve different problems, which at first glance don't seem related, but mathematically are almost identical. So I'm going to try to solve two problems in parallel to show you that what we're doing here with the electric charges can be applied to other scenarios. So I'll start by writing down the scenario for the charges. We're going to have, so this is going to be, let's say, an escape velocity problem. So what we're going to do is we're going to have a large charge, let's say plus Q, and we're going to place it at some position along this dashed line, and that large charge is going to be fixed in place. So this is held fixed in place the entire time. So throughout this entire problem, this charge, capital Q, is not going anywhere. Okay, and then we're going to have a second charge. And we'll place another charge over here. This will be plus little q. And initially, sorry, that's not a plus charge. This is going to be a negative charge. So they're attracted to one another. But what our goal is going to be is to try to arrange it so that these charges never come together despite the Coulomb attraction between the two. And the way we're going to do it is we're going to give little q an initial velocity that is directly away from big Q. And the question is going to be, how fast do I have to make the initial speed so that the two charges never come together? So, how fast must the initial speed V naught be such that Q, or say, let's say minus Q and plus big Q never come together? In other words, another way of saying that is, what is the speed required so that little q escapes the pull of big Q? What is the speed V naught required such that minus Q escapes the pull of plus Q? Okay. Now what we're going to do is very similar to what we just did in the previous problem. We'll write down initial potential and kinetic energies, then we'll write down final potential and kinetic energies, and we'll make sure that we conserve this mechanical energy and then solve for the speed. Before we do that, let me write down the scenario of a parallel problem. Actually, okay, let's say let's just remind ourselves that U for this problem is going to be KEQQ divided by, let's say, R. And I'll put a minus sign in here because our little charge Q is negative. Okay, so here's the parallel problem. Okay, so we're going to have the surface of the Earth here. So this is Earth. And here's the center. This thing has a radius, capital R, the radius of the Earth. And then we put a rocket on the surface of the Earth. And we're going to launch that rocket with some initial velocity directly away from the surface of the Earth. And this is going to be a rocket of mass little m. And the Earth has a mass of big M sub e, let's say. And so the rocket is always going to be attracted gravitationally to the Earth, just like our point charges of opposite sign are always attracted to one another. And so the question is going to be, what is the initial speed required such that the rocket escapes the gravitational pull of the Earth? That is, the rocket never returns back to the Earth. So what is the required speed V0 such that the rocket never returns to Earth? Or equivalently, what someone might say in fewer words is find the escape velocity. What we're going to need to know to do this problem is, first of all, the approach is going to be exactly the same. We're going to write down initial potential and kinetic energies and final potential and kinetic energies, and then we're just going to set them equal to each other. To do this problem, we need to know the gravitational potential energy. The version that you are familiar with will just be mgh. So near the surface of the Earth, the gravitational potential energy just depends on the height from the Earth. But that's an approximation. The true form of the gravitational potential energy, I'll write it as UG, is G. It will be m Earth divided by the mass of our rocket. And then it's just divided by the distance between, say, the center of the Earth and the rocket. There's one subtle difference, is that there's a minus sign in here. And the reason that you get a minus sign, I'm not going to derive it, but we could think about why it's there. The gravitational force, or yeah, let's say the gravitational force between two masses, both masses being positive, it's always an attractive force. Whereas if I have two charges and they're both positive, it's a repulsive force. So the force acts in a different direction. And so that's where this minus sign comes from. You could imagine, like, the way we got to energy is doing a work kinetic energy theorem, which involved the integral of the force. And so if the force has the opposite sign, then we'll end up calculating the opposite sign for the potential energy, and there it is. Okay, so let's do our charges. We'll do on this side, and our rocket we'll do on this side. And so we'll start with initial potential energy. So for our charges, we wrote down the potential energy here. All we have to do is recognize that the initial distance is d. And so this initial potential energy is Coulomb's constant, Q times Q divided by d. And we put a minus sign in there because our little charge is negative. Yeah. Are always, so if you have, say, like a So do you have an example of another attractive force that involves potential energy? No. So the answer is maybe, but the gravitational one is the only one I can think of off the top of my head. Yeah. Okay, so that's for our charges for our rocket. UG initial is going to be this gravitational constant. It's 6.67 times 10 to the minus 11 is its value, times the product of the masses. So we have the mass of the Earth, and we have the mass of the rocket, and then divide by the distance between them. Initially, our rocket is sitting on top of the surface of the Earth, and so it's a distance of the radius of the Earth away from the center. Okay, there it is. The initial kinetic energy for our rocket, for our charge. Let's start with the charge. Remember, we said the big charge plus Q was going to be fixed in place the whole time. So it's never moving. It never has any kinetic energy. All of the kinetic energy in our system is only this little charge minus Q in this case. And so we said we're going to fire it away at a speed v0. And so we take 1/2 mv0 squared is the kinetic energy. And probably what I didn't do is specify that this little charge, has mass m. Okay. For our rocket, the Earth is very massive compared to the rocket, so it's barely moving. So we'll neglect any kinetic energy of the Earth, and we'll have only the rocket's kinetic energy, and so it's going to be 1/2 v naught squared. So those two are exactly the same. Okay. So that's the initial situation, and so we'll go initial here, and then we'll do final here. All right, so just like in the previous problem, what's the final potential energy when the charges are infinitely far from one another? 0. Okay, so this is because R goes to infinity. What about the rocket? The rocket is launched and it gets infinitely far away from the Earth, and so it also has 0 potential energy at the end. Okay, so now we have to think just a little bit, not too much. If I require that the rocket or the charge never turns around and comes back, what is the speed going to be when they're infinitely far away? What's the minimum speed I could have once they get to this infinite distance? I don't want the speed, or let's say velocity. I don't want the velocity to go negative, because that means it'll have turned around and start coming back. So what I want is I want the charge or the rocket to only come to a stop only after it's infinitely far away. So to ensure that the charge / rocket never stops and turns around, we require that v equals 0 only when r goes to infinity. So if the speed became 0 before the distance was infinitely far away, there's still going to be some kind of attraction between the objects, and it'll start accelerating back towards its original position. So we don't want that. If I'm looking for the minimum possible escape velocity, I don't want the rocket still to be flying away when it gets to infinity. I want it to slowly just come to a stop only when it's an infinite distance away. So if that's true, then we would say that the final kinetic energy, I want K final. K final would be equal to 0. K final is equal to 0. Okay, so that's the condition for determining these escape velocities. And then finally, what we can do is we can conserve mechanical energy. So U initial plus K initial is equal to U final plus K final. But a lot of this stuff is 0. The final potential energy is 0. The final kinetic energy is 0. And so that means that U initial, let's say minus U initial is equal to K initial. All right, what was U initial? It was KEQQ divided by D. So I've dropped the minus sign because I want minus U initial, and U initial is minus KEQ times Q over D. And then the final kinetic energy is, the final kinetic energy is 0. The initial kinetic energy was 1/2 mv0 squared, like so. All of this is exactly the same for the rocket. We require minus the initial potential energy is equal to the initial kinetic energy, minus the initial potential energy, which is G mass of the Earth times mass of the rocket divided by the radius of the Earth. And then the initial kinetic energy is 1/2 mv0 squared. Okay. Now, all we have to do is solve for V0 in both cases, and we'll get the escape velocity. So let's start with the charges. So we're going to solve for V0, the escape velocity. Velocity. Okay. So let's see, V0 is going to be equal to, we have to multiply by 2. Then we have KEQ times Q. And we have to divide by M, so we get M times D. And then just take the square roots. Yeah, that looks right. So that's the escape velocity for our charge. There's one subtle little difference for our rocket problem. The one difference for the rocket problem is that the kinetic energy and the potential energy are both proportional to the mass of the rocket. And so that means we could cancel those factors of the mass. And now we solve for V0. V0 will be equal to, multiplied by 2G, mass of the Earth. And then that's it. We have the radius of the Earth, and then we have to take the square root. And so that's the escape velocity for our rocket launch. Okay, and so there's 2 parallel problems, one in electrostatics, one in gravitation, that have basically the same solution or the same approach. The rocket solution is interesting because it doesn't depend on the mass of the rocket. I could have a huge rocket that's very, very heavy, and the velocity I have to give it to escape the gravitational pull is the same as if I was just trying to throw a tennis ball and make it escape the Earth's gravitational pull. Now, of course, we've neglected things. If I launch a rocket, it's going to feel drag through the atmosphere. And so we haven't accounted for those sorts of effects. But this is a rough back of the envelope estimation of how much speed you have to give a rocket at launch in order to get it to leave Earth's gravitational pull. Okay, good. Let's do one more problem. And the problem I want to do is another example. We're going to try to find the electric field vector and magnitude if the electric potential is equal to 2x squared y plus, I don't know, I did something weird, y cubed times pi, okay? So I don't really care what kind of constants or factors you put in there, but let's say this is our potential. So what we have to remember is that the electric field along the direction S can be found by minus the derivative of the potential with respect to S. So what we're going to do is we're going to find the X and Y components of this electric field using this method. That will allow us to construct the electric field vector. And then from there, we could calculate the electric field magnitude. So find the X component. So EX is equal to minus dV dx. So what is that? What is the X derivative of this potential? What's the derivative of 2x squared y with respect to x? Yeah, so it's going to be 4x. The x squared is the only thing that matters. So the derivative of x squared becomes 2x. So we get 2 times the 2 is a 4. The x squared becomes an x. And then we still have this factor of y. And then that's the derivative, but we require the negative of that derivative. So it's minus 4xy. There's a second term, y cubed times pi, but there's no x in there. And so the derivative of that is just 0. Okay, so we're going to find the y component next. So EY is minus dV dy. Okay, so the first term, 2x squared times y, what's the derivative with respect to y? 2x squared. And then we need the minus sign. Okay, and then for the second term, what's the second term? We have the y cubed times pi. 3 pi y squared. And I just put the minus sign in front because we need that negative. Okay, so that means the electric field vector is the x component along the I hat direction times the y component along the j hat direction. And so just putting in the numbers, it's going to be minus, let's see, 4xy I hat plus 2x squared plus 3 pi y squared, and that's in the j hat direction. Where I've just, every single term had a minus sign, so I just took an overall negative sign and put it up front. Okay, so if we were to draw that, let's draw our coordinate system x and y. So our x component is in the negative direction, and so it's going to look something, you know, I don't know exactly what it looks like. It's something like this. Our y component is also negative, and so it's going to look something, I'll just make something up, ey. And then if I want to find the net electric field, it's the sum of those two. Okay, and so the magnitude that we were asked to find is the length of that blue vector, but we formed a right angle triangle here where the hypotenuse is the magnitude we want, and then we have ex on one side and ey on the other side, and so e squared, the magnitude of this squared is just ex squared plus ey squared, and so therefore, this will be the last thing I write down. The electric field magnitude is going to be minus 4xy squared. That's the x component squared. In fact, I wrote the minus sign there, but I didn't have to because I'm squaring everything. The negative squared is just going to be positive. And then the y component would be minus 2x squared minus 3 pi y squared all squared. Again, I put the minus sign in there, but I don't have to because I'm squaring everything, so we'll get a positive result. Nevertheless, this is the magnitude of the electric field. Okay, and then here is our electric field vector. All right, so that's where I'm going to stop. That's a bunch of examples applying some of the things we've been talking about the last couple of classes. On Wednesday, we've got a couple more things to do for this chapter. I think we're in chapter 7 now, but then we'll finish that off, and then we'll probably also start chapter 8 on Wednesday. Yep. Yeah, the dot product of the electric field with itself. Yes. Yeah. It's also here. If I was to do, if I had E is equal to EX I hat plus EY J hat dotted with EX I hat plus EY J hat. If I do I hat dot J hat, that's going to be 0 because they're perpendicular. So it's only I hat dot I hat that survives. And so it's going to be EX squared I hat dotted with I hat plus EY squared J hat dotted with J hat. But these are both 1. And then you get EX squared plus EY squared, exactly what we did. Yeah. Yeah. Just a second.